In this video, I'm going to cover Unit 2, Part 1, Lesson 3 of our calculus class, in which we get practice computing and calculating derivatives of polynomial functions, and we'll also talk about the equations of tangent lines as well as something new that are called normal lines. Now, also in this video, I'm going to practice with the alternative notation for derivatives so that we can see some examples of that. Now, in these examples, you'll notice that the equations are written as y equals some equation. They're not written as f of x. Now, if the function was written in function notation like f of x, then using the original notation for the derivative that we established in the last few videos, I think would be appropriate. But since the equation here is written in y notation, y equals notation, then the alternative or Leibniz notation, I think, would be appropriate. And so you'll notice here, in a sense, we've got three separate mini functions that are being added and subtracted with one another. We've got a constant, a linear function, and a power rule. And because of our derivative rules in the last lesson rather, because of these rules that we established, we know that when several functions are being added together, we could just as easily find the derivative of each function and add or subtract them together. And we've got rules for polynomials and constant multiples and constants themselves. So we'll utilize all of that, and I'm certain by the end of this video you'll be computing derivatives very easily. So let's go ahead and do this. I'm going to use the Leibniz notation. I'm going to call this dy dx. And verbally, we would say the derivative of y with respect to x when we're using this notation, dy dx, the derivative of y with respect to x. Now, in this first function here, 2x squared, we're going to use the power rule. Power rule says to take this exponent and bring it down and multiply it by the existing coefficient. So that's going to turn into a 4. The x remains as it is, and this exponent reduces by 1, and we've got x to the first power. I'll just leave this as 4x. For the second function here, we can do the same thing. We can imagine that there is an exponent of 1. If that exponent of 1 gets brought down to the front, well, 1 times negative 12 is still negative 12. Then we're left with x to the 0 power. But you and I both know that x to the power of 0 is just the number 1, so I don't need to illustrate that. Lastly, for this function, at the end of the larger function is a constant, and the derivative of a constant is 0. Here again, we don't need to show a plus 0 at the end of the rule, and we can stop right here. The derivative function of y equals 2x squared minus 12x plus 17 is simply 4x minus 12. And even with me talking through that and spending almost 3 minutes on that particular problem, that sure saves a whole lot of time compared to the difference quotient method we were using last week. So to continue with this, we need to find the equation of the tangent line at 1, 7. And so what we're going to do next is we're going to evaluate this derivative, the derivative of y with respect to x at an x value of 1. This is part of our derivative notation as well. We use this vertical bar to imply that we're evaluating this derivative at a particular number. And the x value is 1, so we need 4 times 1 minus 12. And that ends up equaling 4 minus 12, or negative 8. So we now know the slope at an x value of 1, or at this particular coordinate, 1 comma 7. We know the slope is negative 8. Now, finally, with the point slope formula, y minus y1 is equal to m times x minus x1. With a little bit of distribution, we've got negative 8x plus 8, and adding 7 to both sides to isolate y, we have negative 8x plus 15, and there is our tangent line at this point. If we were to try to graph this, of course, we could take the y-intercept up here is positive 15, and the slope of negative 8, so we might try this, down 8 and over 1, down 8 over 1. Oops, my screen is sliding all over the place here. But I think from each of these positions, down 8 over 1, up 8 over 1, I think we've got a good representation of the tangent line at that particular point. So if you would please try the next problem on your own. Compute the derivative first, use the derivative to find the slope, and then with the slope and existing point, find the line that is tangent at this particular point. Pause the video now and resume playback in a moment to check your work. And there we have it. The derivative, again using the power rule for each of these terms or each of these mini functions, works just fine. We have negative 4x minus 12 because this 2 times negative 2 is negative 4, reduced by 1, we've got x. This power of 1 times negative 12 is negative 12, reduced by 1, and the x disappears. And the derivative of negative 16, of course, is 0. There is no slope for y equals a constant. So this is our derivative rule that we established right here. With that rule, we evaluated it at a value of negative 3 for x. And so negative 4 times negative 3 is negative 12. I'm sorry, positive 12. Positive 12 take away 12 is 0. So our slope at this point is 0, which visually looks about correct. And as we make our substitution and simplification, we end up with the equation y equals 2. And this line does appear to be tangent to the blue curve at the point negative 3, 2. Moving on, for the remaining questions, this time we're being asked to identify the normal line, or the line normal to a function. This is going to be particularly helpful in our physics class, although understanding a normal line could be helpful elsewhere too. But a line that is normal to a function is perpendicular to the tangent line. So we're going to strike the same point. We're just going to be perpendicular to the tangent line. And in physics, this is important because when we're talking about forces for movement and that sort of thing, it's helpful to know what our perpendicular or normal forces are, especially when considering friction and how that acts on an object in motion. So for number 3, one thing I would encourage you to consider is that this term with x squared over 2 is the same as 1/2 times x squared. And that might help you when looking for the derivative and using the power rule. So if y is equal to 1/2 x squared, then the derivative of y with respect to x is 2 times 1/2, which is 1. So we've got 1 times x, and this exponent of 2 gets reduced by 1, and we've got 1 times x to the first power. We don't need that leading coefficient of 1, and we don't need the exponent of 1, so we'll just write the letter x here. The derivative of this linear rule, well, that's just the coefficient, so we'll write minus 1. Again, we're thinking the power rule. This exponent of 1 drops down and multiplies by this negative 1, and it reduces to 0 and essentially disappears. The derivative of a constant is 0, so I think I'm pretty happy with this derivative here. Now, we're being asked to find the normal line at this point, at 0, negative 5/2, which is right here. If I substitute a x value and x value into our derivative rule, so the derivative of y with respect to x at x equals 0, then this calculation will tell us how steep the tangent line is. And this hopefully makes sense to you. It appears that the tangent line has a slope of negative 1. So that's a better representation. We've got a slope of negative 1 at this point, but that's not what we're after here. We're not after the slope or the equation of the tangent line. What we want is the normal line, and the normal line, of course, has a perpendicular or a slope that is perpendicular to this. And if you recall from your days in either Algebra 2 or perhaps in geometry, in order to find the slope of a line that's perpendicular to another, we would take the slope of the original line, in this case, negative 1. I'm going to write it as a fraction because the perpendicular slope is the opposite reciprocal of the slope that we just had a moment ago. So opposite means to change its sign, and reciprocal means to flip the fraction. So therefore, the slope of the normal line, I'll just use slope of the normal line, is equal to the opposite. So we're going to switch this to a positive slope, and then we're going to flip this fraction over. We'll call that positive 1 over 1, or in other words, the slope of the normal line is equal to 1. And that's pretty much what this dotted line looks like here, so I think we're in good shape. Now that we understand what the slope of the normal line is going to be, we'll proceed as usual. Y minus our y value, which was a negative 5/2, is equal to not negative 1 for our slope, but positive 1 for our slope, because that's the slope of our normal line, and our coordinate located at x value of 0. So we've got y plus 5/2 equals 1x minus 0. When we subtract 5/2 from both sides, we have y equals x minus 5/2. And this line has a y-intercept of negative 5/2, but a slope of 1. And I'll indicate that with the dotted line here, just so that it stands out a little bit from our original work. So the tangent line was here with the solid line. The normal line, or the line normal to the tangent, is shown with a dotted line, represented by this slope-intercept equation. Why don't you go ahead and try the last example on your own. You can pause the video now and resume playback in a moment to check your work. And here we have it. The derivative equation is 2x plus 8. When we use the derivative function to find the slope of the tangent line, we get 2. If I were to write 2 as a fraction, of course, that would be 2 over 1. So the opposite reciprocal of 2 over 1 is negative 1 over 2. Using that slope with a point slope formula, we simplified to obtain a linear equation, negative 1/2 x minus 5/2, which is 2.5, by the way. So we had a y-intercept of negative 2.5, a slope of negative 1/2, and this red dotted line represents the line perpendicular to the perpendicular to the tangent line at the given point. So again, I hope that this video helps to clarify some things as well, or not only the normal lines and the ability to find a derivative, but also the secondary derivative notation. If you have further questions, please let me know. Otherwise, thanks for watching.